Welcome back, boys and girls. Here I am in my yellow shirt on the 21st of April, going to talk about our last topic on our syllabus, which is the topic measures of association. First, some preliminary things. Uh, Next class on Thursday, I'm going to do a review video, so I'm not going to introduce any new stuff, and I'm going to look back at the semester and try to give you a way to summarize the semester and where we've been and how we've done. Then what happens is that the deans have interceded again about how we do our final exam. The deans have decreed, and these are important people, we got to listen to them, they have decreed that you can't hand out a take-home final before May 4th, which is the final exam period. Good, I'll do that. On May 4th, I'll hand out the final exam. I'll email it to you. Now, the deans also tell us that a take-home final can't be due before May 12th. I don't know how they arrived at that, so we'll do that. I'll hand it out May 4th, and then on May 12th, it's due by midnight, your take-home exam. And then you're done for the semester. Try to make the most out of this very unusual situation. Now, let's launch into today's topic, measures of association. Let's put it in a context. We did that cycle of research where we start out with problems, we do a research design, we carry out measurements that produces data, we have to analyze our data. Now, we saw the simplest way to analyze the raw data that we generate through our research design is through univariate analysis, where we take one variable and we look at what is the typical case like. We did measures of central tendency, and then we want to know how spread out are the cases from the typical case. Those were measures of dispersion, okay? Then we move up to the next level of complexity. We take two variables together and we want to analyze their relationship. The first question we ask is this: are there grounds for a rational person, and they mean a mathematician, are there grounds for a rational person to think out in the population there's a relationship between these two variables? There's a whole group of statistics that answer that question. Would a rational person think that out in the population these two variables are related? They're called tests of statistical significance. Last time we did the simplest one, chi-square, which is used when you have two variables at the categorical level of measurement, and you put them on a cross-tabulation, and you ask the question, the null hypothesis says these two variables are not related in the population. Would a rational person reject that null hypothesis? And we didn't go into different kinds of tests of statistical significance, but there are many others, and the proper one that you choose depends upon that level of measurement that's so important, the level of measurement of your variables. That different levels of measurement contain more information than others, and so we can use different, more sophisticated statistical techniques. Okay, so you do your test of statistical significance, you find out, I can reject that null hypothesis. There's a relationship between these two variables. Analysis doesn't stop there. Then we want to ask, how strong is this relationship between these two variables? And in what direction, if there's directionality to it, like it's at the interval ratio level of measurement, there's directionality. This variable can go up as this one goes up. That's a positive relationship. But it's also a very legitimate relationship if this one goes up and this one goes down. That's a negative relationship. We call that directionality, and it applies when you're at the ordinal or at the interval ratio level, not the categorical level. The categorical level just places objects into different categories. Now, let's go into measures of association. The mathematicians have exploited something called the principle of the proportional reduction of error, meaning this. Here's their idea. You have variable 1 and variable 2, and we're always trying to predict what values are on variables. That's knowledge, right? We want to predict we have 300 people, say, and variable 1 is, did they vote in the last election? We know we got these 300 people, and they either voted for Madam Secretary Clinton or President Trump, right? And we want to predict for those 300. which one did they vote for? And we're told half of them out of the 300 voted for Madam Secretary Clinton and half voted for President Trump. Now, we try to predict for each person, who did they vote for? And we're not told anything about them and we can't see them. And we have to predict. And to give you some incentive, say you get $50 for every one you get right. That's incentive, isn't it? I mean, get 300 right, 350 buck notes with US grant on them would be nice. So let's do this. Let's say we got, what would a rational person do for the 300 of them? You got to, and all you have is they have a serial number on a list, and you got to put down voted for Madam Secretary Clinton or voted for President Trump. What would a rational person do on that list of 300? We're going with IDs from 1 to 300. You don't know anything about them. Well, the mathematicians will argue it doesn't really matter since 50% voted for Madam Secretary Clinton and 50% voted for President Trump. It doesn't really matter what choice you make for any of them. It's just all random because you don't know anything about them. Now, the person that's doing this guessing is going to get 50% of them right. So they'll get $50 bills, right? That's what our expectation is. Now, the principle of the proportional reduction of error says, let's do the same thing over again, but now we're going to tell you one thing about each person, and then you got to guess if they voted for Secretary Clinton or for President Trump. And if that knowledge of that second variable helps you reduce the errors you made, you got 50% wrong the first time, we can exploit that. And that can tell us how strong is the relationship between those two variables. That's the principle of the proportional reduction of error. And in order to help us do that mathematically, the mathematicians have made up a number of measures of association. And the proper one you choose is, like almost all these choices in statistics, it depends upon the level of measurement of your variables. There's different measures of association when your variables are at different levels. So I made up a chart here of some of the three measures of association we're going to look at. We're going to look up here. And we have over here the level of measurement, right? And then here is the measure of association that would be appropriate for it. Now, we start out at the lowest level of measurement here, the categorical nominal level of measurement. And we see that the statisticians have come up with a measure of association called asymmetric lambda. And we're going to talk about that. If you were here and we were doing our computer assignments, we would be getting SAS to generate an asymmetric lambda for us, but we know COVID-19 interfered with that plan. Now, we go down to the next more complex level of measurement, the ordinal level of measurement down here, right? And we see that the mathematicians have come up with a proper measure of association called gamma, which is appropriate to use at the ordinal level of measurement. And it exploits that at the ordinal level of measurement measures something along a spectrum or a scale. So there's more information contained in it. We'll talk about gamma. Again, we would have had a computer assignment number 4, we would have had SAS generate some gammas for us. And then down here, we have the interval ratio level of measurement, the highest level of measurement. And we see that there is, utilizing the principle of the proportional reduction of error, we have Pearson's correlation coefficient, which is designated R, just like X bar is the mean and S is the standard deviation. R is Pearson's correlation coefficient. And so what I'm going to do is I'm going to show all three of these and give you an idea of how you interpret it. Now, let's go to this asymmetric lambda. That means when we're dealing with asymmetric lambda, we're dealing at the categorical level of measurement. And that's the lowest level of measurement. There's not much information contained in it. And this is how asymmetric lambda is defined. Asymmetric lambda is defined as the reduction in errors over the original errors that you made. And the idea with our example, with trying to predict how people voted for Madam Secretary Clinton or for President Trump, it's this. If the first time we try to guess whether people voted for Madam Secretary Clinton or Trump, and we just got their serial numbers, we don't have anything about them, we'll get 50% wrong, right? Those are our errors. Those would be the original errors we put in here. So we would expect to get 150 errors originally, right? Now, Let us say we have knowledge of a second variable. What variable would help us predict? Well, you think of it as yourself. You want to make $50 for every one you get right. What one piece of information from every person there could you ask them that would help you do better and reduce your errors? You get more of those general grant notes. I would say a real good one to ask is for each person find out what party do they belong to or they identify with, the Republicans or the Democrats. Oh, that's a big deal. That's good then. What would happen is, as a person, as you got to look at the first person, you would be told they were a Republican. And you would guess, aha, they voted for Trump. And any people that marked down that they were Democrats, you'd say they voted for Madam Secretary Clinton. Now, the question would be, did you reduce your errors? Well, you would reduce your errors tremendously because Democrats tend to vote for the Democratic candidate and Republicans tend to vote for the Republican candidate. And so that would be the second time through, you're going to find out how many errors. You reduced your errors by how much. And this would give you a measure of how strong the relationship is. Imagine if you reduced your errors completely and you got everyone right the second time. This would be, you get an asymmetric lambda of 1.0. 1.0 is a perfect asymmetric lambda. What if you didn't reduce your errors at all? You just did just as bad the second time as the first time. You would then get an asymmetric lambda of 0. So here's the way to interpret an asymmetric lambda. It runs from 0, where there's no relationship between these two variables. And as it gets stronger and stronger, you're reducing your errors. You're doing better and better. And 1.0 would be a perfect relationship in asymmetric lambda. And that's how asymmetric lambda works. Now, let's go up to our next one. Let's go up to the ordinal level of measurement. What measures of association do we have? We have a measure of association called gamma. And this is how gamma works. Gamma is a proper measure of association when you have two variables at the ordinal level of measurement, where they're measured along a spectrum of some kind. And gamma is equal to C minus D over C plus D, where C are concordant pairs and D are discordant pairs. What that means, what you have to do here is, if you have 300 people, as in our example here, you take the first person in this, well, you couldn't do it with how they voted, right? Because now we need an ordinal level of measurement to do it. So where we have an ordinal level of measurement, that example where I gave you those two variables are not ordinal, so we can't use that one. But think in your mind where you have the amount of something. Let's say you have, you have people's LibCon score, where they're liberal or conservative, going from 0, where they're left of center, all the way to 7, they're right of center. And then at the same time, you have Bush on the thermometer scale, running from 0, I hate the guy, up to 100, I love the guy, something like that. Or take Trump, of all people, because people have strong feelings about Trump. You would have people on the thermometer scale running from 0 to 100. Then what you have to do is you take the first person and the second person, and you look at, did their variable 1, they moved up? What did they do on variable 2? Did it move up also? That would be a concordant pair. Then you compare the first person to the third person. On that one variable of LibCon, they moved up. But on this other one, on the thermometer scale, they moved down. That would be a discordant pair. Then you compare the first and the fourth, the first and the fifth. Then you got to go back and do the second and the third, the second and the fourth. Look at all these comparisons. There's tens of thousands of comparisons going on. Luckily, we have the computer, which will add up how many concordant and how many discordant pairs there are. And the thing to do is a gamma is generated by software now. We don't do these things by hand. I didn't graduate as a graduate student. That was because the mathematicians, they love to do this kind of thing by hand. And ultimately, you've got to say the computer software is written and encoded into it is what the mathematicians have learned about these sorts of things. So what happens with gamma when you get a gamma between two variables? Well, where there's a perfect negative relationship. A perfect negative relationship is going to be when when all of them are discordant. Every time this variable moves up, the other variable moves down. And it happens every time. That means the c's are 0 there, and you get negative d over plus d, which is a negative 1. Negative 1 is a perfect negative gamma. That means every time this variable moves up, this variable moves down every time. So that's where the negative comes from, that they're discordant. They move in the opposite direction. And the 1 is it's the perfect relationship. What happens is you go from negative 1, you get closer and closer and closer. As you get to 0, there's really a weak or a 0, no relationship at all, but you keep going in the positive direction. You get positive 0.1, positive 0.2. It gets stronger and stronger until you get to positive 1.0. Positive 1.0 is every variable, every pair that we compare concordant. So these are 0, and you get C over C, which is 1 plus 1.0. That's a perfect positive relationship. Every time this variable goes up, that variable goes up. And that's how gamma works. Again, we get something like SAS to do this calculation, because it's very tedious to do this calculation when we have to do it by hand. Now, finally, let's go up to the highest level of measurement, the interval ratio level of measurement. And this is the area that mathematicians love, because there's a lot of information contained in it, and there's a lot of very sophisticated modeling techniques that can be used when you have interval level variables. When you have two interval level variables, the proper measure of association is called Pearson's correlation coefficient, which is designated by the letter R. It's used so much it has its own standard letter that stands for it. Now look at this is how Pearson, remember Pearson? Pearson was the mathematician who did chi-square and calculated that. Well, he went on after he did that and did something more sophisticated. He has Pearson's correlation coefficient, and it's the relationship between two interval level variables. Let's look at it. Pearson's R between the variable x and y is equal to, and then look at all this, the summation of I running from 1 to n, where you take each case and get its x score and subtract it from x bar, and then for each case, since there's two variables, you got a y, you take that y and subtract that thing, and you work it out, and you do this long calculation, and what you get out of that, you put the denominator of n minus 1 times the standard deviation of x and the standard deviation of y. What you get is, it's harder to figure in your mind. How does this thing work? But there are some simple rules that you can define how it works. And what happens is that Pearson's correlation coefficient is just like gamma. It runs from negative 1, which is a perfect negative relationship, all the way it gets closer to 0. As you get closer to 0, the relationship is not strong at all. Then you move in the positive direction away from 0, and you get all the way to the highest Pearson's R in the positive direction is plus 1.0, which is a perfect positive relationship. What this mathematical formula is doing is it's trying to say how close to a line are the scatter plots when you plot these two variables. So for instance, I'll give you some scatter plots over here. This is a scatter plot here of a Pearson's correlation coefficient of 0, meaning there's no relationship between the two variables. And look at how the scatter plots. It's just random patterns here. If you know somebody's y value down here and you look up, you can't really predict their x value because they're all over the map. Well, what happens is, as these scatter plot dots get closer and closer to a line, running in the positive direction, the line runs up from left to right, you get closer and closer to 1.0. So here is a Pearson's correlation coefficient of 0.40. There's still a lot of mess here. They're all over the place, but they're beginning to squeeze down to form a line. Then you have plus 0.6. Here's that one here. And then plus 0.8. Look at that, look at how it's forming a line here. Then you have plus 0.9, closer to a line. And look at, this is plus 0.95. Look how close to the line those dots are. And I can tell you in social science, plus 0.9 is really that's a high Pearson's correlation coefficient. We're usually happy with the relationship of like 0.5. So something, looking something about like this one here. Meaning, well, if you look at the y variable here, you can give kind of an idea of where the x is, but there's a lot of other slop built into it. Now, these are all positive Pearson's correlation coefficients I gave you. And then we can look here at, I have some negative Pearson's correlation coefficients here on this page. And if we look at this page here, here we have a negative 0.30. Now, in a negative Pearson's correlation coefficient, the line falls from left to right. That is, as this one variable gets bigger, the other variable gets smaller. This is negative 0.30, negative 0.5. We're trying to see a line pinch down here. Negative 0.70. So you can see the falling line in negative 0.70 here. Then we have negative 0.90. That's a strong negative relationship. And then we're down to negative 0.96 here. And look at this. This one here is negative 0.99. Look at how close it is to a falling line that you're going from left to right. So that's Pearson's correlation coefficient. And the thing to know about it is that it runs all the way from negative 1, which is a perfect negative relationship, gets closer to 0 as the dots spread out and the relationship is not strong or non-existent. And then as we move away from 0 in the positive direction, it gets stronger and stronger as we have a rising line at plus 1.0. That's how Pearson's correlation coefficient works. And I wish we were meeting together. We could look at these things in SAS and see how they work and generate them. People don't do these things by hand anymore, but doing them by hand and looking at the formulas helps you understand what exactly the computer is doing and how it works. Because the computer will crunch the numbers, but ultimately you are the person and you are the thing that has to make the decision. How do we interpret this and how does the world work? So that's all I have to say about measures of association. Tune in Thursday and I'll look at the whole semester and how you should kind of analyze and stand back and look at where we've been and what we've done. Thank you, and I hope you're enjoying yourself.